Good morning, students. Today, I'm going to record a video to go over some of the other homework 8 types of problems. We've already discussed, piecewise functions and transformations. But today I want to talk about transformations just a little bit more, and then go into a new topic that has to do with constants of variation. So if you recall, we actually did quite a few transformations examples in the last video. We've got one example left and then a repeat example that I want to do real quick. But let's start with question 18, which is from the Homework 8A Common Version. In this example, the graph of a function g is given in an image, and we want to identify the parent function and then try to figure out what was done to this function to transform it from the parent into the graph that we're looking at now. So this is pretty obviously the graph of a parabola, and I hope it's fairly obvious that a parabola graph is an x squared parent function. So these parent functions you need to memorize. Parabolas are x squareds. So our first part of our answer here is x squared. The next questions they're asking are about what g of x looks like after transformations. So if g of x started out as the parent function x squared, what have we done to x squared to transform it to the graph we're looking at now? So I'm going to write it like this with a bunch of space, and we're going to try to fill in some transformations. Now, you'll recall a few transformations we've already talked about. For instance, if there's a negative out front, that would reflect our parabola over the x-axis. But our parent function, which would look something like this, I'm going to try to draw it accurately here. Parent function would look something like this, hasn't been reflected. So there is no negative out front. The next thing we would look for is a stretch or like a condensing. So has our function gotten shorter and fatter, or has it gotten taller and skinnier? And if you look at your parent function, the parent function of x squared always goes through 1, 1 and 2, 4, which I didn't do a great job of drawing here. Also, on the other side as well, -1, 1 and -2, 4. If you look at the new function that we're dealing with, that doesn't happen here. It would go here, here, and here, here, and here, if it were to match exactly. But it doesn't match exactly. It has gotten shorter and fatter, so to speak. So let's figure out how much shorter and fatter. Well, if our original parent function would have been a 2:4 ratio, but it's now, I need to erase this, but it's now a 2:2 ratio. Let's draw it this way, 2:4, and now we have a 2:2, then our height at this point essentially has gone from 4 to 2. Which means it's cut in half, or it's divided by 2. So in front of our function, we would throw a 1/2. That's because it's been condensed by a factor of 2. We've divided this length by 2, or this height by 2. All right, now let's deal with any shifting. So our parent function, which was centered at the origin, has been shifted right 2 units. And remember, when we're shifting left and right, we always do the opposite of what we think we're going to do. So normally we would think of right as plus, but we'll do the opposite, which is -2 inside the function. And then it's been shifted down, 1, 2, 3, 4, 5, 6, 7, 8 units. And this is exactly what you would think it would be. I said that and then I wrote the wrong thing. Since we've shifted down 8, we just throw a -8 on the outside. So here is our g of x. after we've done all of our transformations. So we would take this and write it in the box here the best way we can. Looks like 1/2 times the quantity x minus 2, all squared, and then minus 8. So they're asking a few other things about parabolas here. This first question, question C, identify the concavity of G. I would assume that that's something you all have talked about before in class, but I'll remind you that concavity has to do with the bowl shape. Concave up is like a bowl facing up. Concave down is like a bowl facing down. So concave up, concave down. Another way to think of this as positive or negative. For instance, a positive x squared versus a negative x squared. And that has to do with, reflecting over the x-axis, things like that. So this is a concave up parabola. They want you to identify the end behavior. Well, as x is going to negative infinity, our y value is going up to positive infinity. As x is going to positive infinity, our y value is going all the way up to positive infinity. So our end behaviors, both ends are going to positive infinity. They want you to identify the vertex. This is just a point. So find your vertex, +2, -8 is listed as a point. The axis of symmetry, I'm going to erase some of these mini marks I've made. The axis of symmetry is a line, but it's exactly where you think it is. It just is this line that goes right straight through the middle. Notice that when I draw this line, the left-hand side of my graph and the right-hand side of my graph are perfectly symmetrical around this axis. That's why it's called the axis of symmetry. So the axis of symmetry is just the line x equals +2. And then they want you to identify things like the x-intercept, the y-intercept, the local max or min. That's the same as a vertex. So you're looking for the minimum, which is going to be the very bottom point, the minimum. And the domain. Domain should be fairly easy. It's just going to be all x values from positive to negative infinity. They want you to identify the range as well. Well, for our range, we're obviously, we've got arrows that go up forever. So our range is going to go up forever, but it doesn't start until right here. Let's use a different color. So our range starts here and then goes up all the way to infinity. So our range is going to have a square bracket, start at -8, go up to infinity, and then a parenthesis because you never have a square bracket around infinity. Okay, so that was the last example of transformations. However, I realized in hindsight I made a mistake in one of the problems from yesterday's or from our last class's video. It was question 12 where we were trying to transform a square root function. So I made my mistake because I forgot parentheses where a set of parentheses was really, really, really important. We have talked about reflection. If you reflect over the x-axis, we do that by putting a negative out in front of our parent function. If you want to reflect over the y-axis, so a left-right reflection, you put the negative sign inside the parent function. But I forgot, and I feel really silly for this, that when we do that, when we put that negative inside the parent function, it requires us to throw an extra set of parentheses in there. And it's kind of hard to see until you're actually doing an example. This is the parent function, f of x equals the square root of x. But to transform this into the purple graph, we are going to, I guess they call this f of x, we are going to need to throw some extra things in here to transform it. So g of x, I'm going to write like this, with a big square root and our x inside, and leave plenty of space to add extra features. So let's start with reflection. That's usually the first thing we look at. If we were reflecting f over the x-axis, it would then be down like this. So it would be upside down, so to speak. But that isn't what's happening between f and g. We are actually reflecting f the other direction, we're reflecting it over the y-axis. And it's the first example we did where we saw this, maybe the only example we did. But since this is a y-axis reflection, the negative sign needs to go inside the parent function. So that would be right here, inside of the root. But the thing I forgot about in the last time I did this example is very important. That's going to create a set of parentheses right here. And I'll explain why that's important in a second. So now let's look at our other features. Do we have any stretching or condensing? I don't think so. This looks pretty standard to me. It looks like we go through the points 1 here, 2 here, 1 here, 2 here. This still looks pretty much the same. So no stretching or condensing. Now let's talk about shifting. We've shifted 2 units to the left. So 2 units to the left inside of our function would actually be a positive 2. It's the opposite of what you think it would be. And then we shift 3 units up, which is exactly what you think it would be, a plus 3 here on the outside. So now let's talk about why those parentheses were so important. See this negative sign inside? We would have to distribute it through the parentheses. So this would become a negative x minus 2, like this. And typically, when we look at shifting, you might be surprised and think, well, now it looks like a minus 2. Why would we go left if it's a minus 2? And that's because if it's a minus 2, actually, we go right. So imagine going right 2, up 4, but then, because of this negative sign, we reflect across the x-axis. So what would start here would get reflected. So it actually is a right shift that becomes a left shift when this negative sign requires us to reflect it over the x-axis. So the moral of the story is, do not forget your parentheses here like I did. Obviously this is something that is pretty easy to make a mistake on. So it can happen, and I won't blame you if I ever see this on a homework. I get it. I made this same exact mistake, but I just wanted to caution you to watch out for that. So this is the correct answer. It is not a mistake that I made the first time around. So yeah, caution. Okay, that said, we have concluded our review of transformations. What I'd like to do now is move on to an entirely different topic, but it's a short one. This topic only has a few problems on your homework, and it has to do with constants of variation. We often will use the letter K for constant. You'll see C a lot of the times too, but you can use any letter for constant. So you might be working on problems where they use basically any letter under the rainbow to stand for constant, but we're going to use K. I've got 2 new definitions to throw at you. If a word problem tells you that 2 variables vary directly, then we can set up this type of equation for some constant K. Now K is a constant, which means K is a number. It's some kind of numerical representation, and we should be able to find it using the problem, using the information we're given in the text of the problem. And that's often our goal, is to figure out what K is, so then we have a formula. So that's direct variation. You can set up some relationship between y and x where x is just being multiplied by a value K. On the other hand, this new definition down here, if you have inverse variation, if y varies inversely with x, then the relationship you would set up would be an inverse relationship, which means y and x would be related in this way, y and 1 over x. But then, of course, there could be some kind of constant here as well, and just like in direct variation, we're going to be looking for K in these problems. So really the only reason you need to know these 2 expressions is because they'll help us start our problems, but our goal is always going to be to find K. So let's talk about an example. This is question 19 from homework 8A common version. This question says that the wind farms in Southern California contained wind generators whose power production varies directly with the cube of the wind's speed. So we're going to call power production, I'm just going to call that P. And the wind's speed, I'll actually call that V for velocity. I hate using the letter S because S looks like 5, so I'll use V for velocity. But since it's the cube of the wind speed, it's actually V cubed. So if P varies directly with V cubed, we would write that like this. P equals KV cubed. So this would be like y equals kx, but instead of y and x, we have p and v cubed. So we're actually using our expressions that we learned above to start us off on this problem. Part A asks us to find the exact value for the constant of variation k. So that's our goal. To do that, we're going to use the other information they give us in the problem. They tell us that the generator, one such generator produces 596 power and 22 miles per hour wind. So 596 is P and 22 is V. So if we go plug that in, 596 equals K times 22 cubed, we can now use this to figure out what our constant of variation K is. So it's calculator time. I don't feel like cubing 22 by hand. I wasn't prepared. I didn't have my calculator out. All right, 22 cubed is 10,648. So I'll rewrite this as 596 equals 10,648 k. And then to solve for k, we're going to divide both sides by 10,648. Calculator time again. 596 divided by 10,648 gives us about 0.056. I got 0.05597. And I don't know if they say round your answer to the nearest something. It says find the exact value. You're not going to be able to do that. You're not going to be able to find an exact value because this is a never-ending decimal, it appears. So you're going to have to round. And so rounding to 3 decimals is probably appropriate, which is why I entered my answer as 0.056. For part B, now we're going to use your variation equation. This is very important language. Use your variation equation. Your variation equation is still going to have 2 variables in it. Every variation equation will have 2 variables. So what we're doing essentially is we're going back to our original equation and we're replacing k with the k we found. But P and V go back to being variables. I see students confuse that a lot. They want to still keep P as 596 and V as 22. No, those values are gone now. That was just a single example we used to figure out what K was. But now we need to go back to having P and V as variables with our newly filled in K here. So for part B, we use this as our variation equation. And we need to determine how much power, so that's this, how much P will be generated by a wind speed of 32. So if our wind speed is 32, we can plug that in. So we'll have P equals 0.056 times 32 cubed. I'm sorry. It's early. I made a mistake. Okay, so we're going to cube that, not square it. That's silly. And I'm going to plug in 0.056 times 32 times 32 times 32. That gives me a power of 1,835.008. This can safely be rounded to 1,835. So problems like these are often going to have two parts. First, you have to find out what k is so that you can get your variation equation, and from there, you can use your variation equation to solve a more specific problem. Let's move on to the next example, which is going to be similar but slightly different. In question 13, we're told that the demand for running shoes varies inversely with the cost of the shoes. So we're going to set up an inverse variation equation, which normally comes in the form y equals k times 1 over x. But instead of y and x here, we're going to have demand and cost. So we'll write it like this. Demand equals constant of variation times 1 over cost. And the problem also tells us when the price is set at 40, that's our cost, the manufacturer ships 6,185 orders, that's the demand, per week to retail outlets. So we can actually take those two values and plug them in, and that will help us find our constant of variation. So we'll have 6,185 equals k times 1 over 40. And to solve for k, we just need to multiply both sides by 40. Pulling out my calculator, 6,185 times 40 gives us a big number, 247,400 is our constant of variation. So that's our answer right here. For part B now, we first need to use our variation equation. So we're going to start by rewriting our variation equation. But we know what k is now. So we're going to put that in, 247,400 times 1 over cost. This is our variation equation. Now we can plug anything else we want to in for D or C to figure out what the other one is. So in this next part of the example, we are told that we want to determine the price when demand is 4,948. So we'll plug 4,948 in for D. And we want to solve for C. So the first thing we need to do, since C is in our denominator, is multiply both sides by C. That's going to put C in our numerator, which is where we want it. So we have 4,948C equals 247,400. Then to get C by itself on the left, we're going to divide both sides by 4,948. Again, this is a job for a calculator, so divide this by 4,948, and I get exactly $50. Well, that's convenient. We just plug that in right here. So easy enough. The next example, I'm pulling from question 2 on homework 8A common version. And this one has a bit more going on. We've got two variations in the same problem. So we've got the resistance of a wire varying directly with its length and inversely with the square of its diameter. We have two different variations in the same problem, but this is not as complicated as you think it will be. So if the resistance of a wire, if we call that R, if R varies with anything, there's going to be some constant K multiplied by a direct variation gets multiplied to the constant. So direct variation like length, we would put at the top, and inverse variation like the square of the diameter, we would put at the bottom. So notice I created a fraction here. My direct variation is on the top of the fraction, and my inverse variation is on the bottom of the fraction. So that comports with direct variation and inverse variation kind of at the same time. All right, so now let's use the problem to fill in some of these values to see if we can figure out what K is. So the question says that 80 meters of wire with a diameter of 0.01 has a resistance of 64. So if we plug 64 in for resistance, 80 in for length, and 0.01 in for diameter, we're looking at this equation now. Let's solve for K. You can do this in so many different orders. I'm going to start by multiplying both sides by 0.01 squared over 80, just multiplying by the reciprocal. That's going to basically just give me K on the right, because all of these things are going to cancel. And then on the left, I've just got this kind of nasty expression that I can plug into a calculator. So 0.01 squared is equal to 0.0001. And then if you divide that by 80, you get something very small, and then multiply that by 64. We're looking at 0.00008. And I just let my calculator do all of that hard work for me. So we found our K. That's your solution to part A. Now part B is going to ask us to use our variation equation, use your variation equation, which will now look like this. R equals 0.00008 times L over D squared. We replace our constant with the new value K, and we want to determine the resistance. So find R when we have 90 meters, that goes in for L, with a diameter of 0.03, that's going to go in for diameter. So R equals 0.00008 times 90 over 0.03 squared. Calculator time. So times 90 divided by 0.03 squared. I end up with the number 8. When I plug all of this into your calculator, make sure you put parentheses where you need parentheses. And 8 is in fact our answer, so R equals 8. So these problems aren't so bad. Really, the only trick to the problem is remembering how to set up inverse and direct variations at the start, and from there out, it's just plugging and chugging and finding K and then plugging numbers in and getting a solution. So that is the end of this video. That concludes our conversation about constants of variation. So at this point, you should have everything you need to complete Homework 8A personal version and Homework 8B personal version.